Assalamu alaikum, my dear students. How are you? Hope you will be fine and okay. I'm your teacher Muhammad Ikram, and I welcome you all into my today lecture. Today lecture is about the binding energy, and it is part two. Yeah, you know that in the beginning, in the previous lecture, I told you that actually the mass defect and binding energy were considered to be a single topic because they are very much related to each other. But I told that at that point we needed some introduction to the nuclear physics and to the and about the structure of the nuclei. This is why most of the time I spent it there in introducing to you to the structure of the nuclei and the size of the nuclei and some properties of the nuclei. And then I explained to you the mass defect also. And if you remember that I told you that mass defect is the missing mass when nucleons are combined to form a heavy nucleus. And then I told that some of the mass which is destroyed during this process is converted into energy according to the Einstein mass energy equation. Then right now it is the good time to start with the binding energy rate. What is binding energy? Let me just give you a kind of a brief introduction, and then I will explain to you the bits and bytes of all this topic. Binding energy is in fact the amount of energy required to separate a particle from a system of particles or to disperse all the particles of the system. Uh, Let me tell you in short that binding energy is in fact the amount of energy. It is the amount of energy required required to break or make the nucleus. To break or make the nucleus. This is called the binding energy. Here, so look, if we just separate the system of the particle, then the amount of energy released during this process is binding energy. The question is that why energy is released, and you need to remember this part, and I will explain. Let me start from a very simple example. For example, the hydrogen 2 nucleus composed of one proton and one neutron, that is deuterium. When they can be separated, when we can completely separate when we supply the energy equal to 2.3 MeV, 2.3 MeV per, that is the system. If you provide the 2.3 million electron volt of energy, and I told that 1 electron volt is equal to 1.6 into 10 to the power minus 19 joule, and MeV means million electron volt, so 2.23 into 10 to the power 6 electron volt actually. But on the nuclear scale, energies are usually measured in MeVs rather than in joules because they are small. Now, conversely, when a slow-moving neutron and protons, when they combine to form the hydrogen nucleus, then what will happen? Then the 2.3 MeV energy will be liberated in the form of gamma radiation. So this is why I told that binding energy is the amount of energy required to make or break the nucleus. Now let us come to the reason, that what is the reason, and the reason is simple here. The reason is that the mass of the bound nucleus, the mass of the bound nucleus, the bound nucleus means combined. The mass of the bound particle is less than the sum of the mass of the separate particles by an amount equal to the binding energy. And if you remember my last lecture, I told you, rather I asked you a question that why the mass of the nucleus is less than the sum of the mass of its constituents. And then I told that when the nucleons are combined to form a nucleus, then some of the energy is converted, some of the mass is converted or destroyed into energy. That was the transformation of mass into energy. And where the missing mass goes, that converted into energy according to the Einstein famous mass energy equation, E is equal to mc square. I'm sorry. Okay, so now let me explain all these things to you in great detail. That all the nuclei, we have two kinds of nuclei. One we call the stable nuclei, if you remember, the stable nuclei, and the other we call the unstable nuclei. The unstable nuclei, you can use the word atoms, right? But here we don't study atomic physics. Here we study nuclear physics. So better to write the nuclei. Now you see that what are the stable nuclei? If you remember that I told that stable nuclei are those nuclei which has the N by Z ratio, neutron to proton ratio, are usually equal to 1. Right? They are equal to what? They are equal to 1, and they have their potential energy is, such nuclei have the potential energy is at the lowest level. It is at what? It is at the lowest level. Their potential energy is what? At the lowest level, and they usually do not radiate nuclear radiation. Nuclear radiation, such as helium, iron, or like that. They are sodium, iron, many more, as I told, helium. They are usually stable nuclei. Their potential energy is at the lowest level. Now you will be asking me that why, where does that energy comes in the nucleus? So that is another question, and I'm coming to that question right now also. Contrary to this, we have the unstable nuclei. That what are the unstable nuclei? In case of the unstable nuclei, the neutron to charge ratio is not equal to 1. And uh, they are usually heavy nuclei. They are usually what? They are lighter nuclei. And they are usually what? Heavier nuclei, right? They are heavier nuclei and they radiate energy. Yeah, they cause radiate energy. Energy is not only necessary, I may write radiate nuclear radiation, because alpha and beta are not energy. Nuclear radiation. Why? To move, the reason is what? To move towards greater stability, to move towards greater stability. To move towards what? To move towards greater stability. Now, again, a third question. Every question I remember. A third question, why they want to move towards a greater stability? Because universe uh, just tends to move towards a greater stable order, towards a greater stability. So this is why the elements also. So, and that is the greater stability means to the level lowest state of potential energy. Lowest state of potential energy. Now, the question is why they radiate and how all these how all these related to the binding energy. The emission of what? The emission, the emission of energy, the emission of energy by unstable, by unstable nuclei, by unstable nuclei is due to is due to is due to the fission is due to the fission of radioactive changes of radioactive radioactive changes that occur inside the nucleus. Now, again, coming here, because now I will explain your question one by one. Let us consider, for example, a helium nucleus, right? You see that this helium nucleus has two protons and it has one neutron. This is neutron and this is proton being charged particle. Now, you know that there is the question that the question is that why inside the nucleus the protons live together in a range which I told, for example, the normal radius of the nucleus, if you remember, that was something like of the order of 10 raised to the power minus 15 centimeter. That within the range, the charged particle are so much close together. The question is that why are they the cousin that they live together? They both have positive charge on them and they repel each other. So if they repel each other, how they can be together in such a small space? What does this mean? Either the laws of physics, the Coulomb's law, is not correct, that like charges repel each other, or there might be other explanation. So for your satisfaction, the Coulomb law is almost wonderful. And it is correct. Why? Because it is experimentally proved. Then there might be another reason. And what is another reason? Then another reason is the reason of that there exists strong nuclear force inside the nucleus. Strong nuclear force. There is what? There is a strong nuclear force. Sometimes we call that force as short range. Short range. Why? Because it only acts within this range only. If the nuclear size grows, the short range force become weaker, the strong nuclear force becomes weaker. So it is this force due to which these nucleons are bound together, right? They are being held by this force, right? This strong nuclear force, it is charge independent. What? This force is what? This nuclear force, this nuclear force, it is charge independent force. It is charge independent, charge independent force. It is between NN, between means neutron, neutron. It is between PP. It is between NP, NNP, right? So God created neutron inside the nucleus so that to counterbalance the Coulomb repulsive force, right? So this is one of the reason that hydrogen do not have any proton, any neutron in its nucleus. Why? Because there is only one proton. So there is no Coulomb force inside the nucleus. So no neutron is needed perhaps, right? So that is one of the reason that the nuclear force is independent of the charge. Thanks to God it is. And it is between NN, it is between PP, and it is between NP. It is this nuclear force which keep the nucleons bound together. So there is a constant fight between Coulomb force and the nuclear force. The Coulomb force tries to smash the nucleus, and while the nuclear force tries to maintain the nucleus. Who wins? It depends, right? As the nuclear size grows, then what happens? The Coulomb force wins, right? The Coulomb force what? The Coulomb force wins, and the nuclear force that is decreases and the nucleus breaks. So in order to provide greater stability, the nature automatically increases the number of neutron in the nucleus. This is why you might have seen in all the heavy nuclei, the number of neutrons are more than the number of proton. Why? To provide greater nuclear force to keep that heavy nucleus stable or at the lowest energy level, right? But unfortunately, as the number of particle increases, then if you remember, one day I told that the size of the nucleus is the size of the nucleus is R naught into A, and the size of the nucleus is R naught into A power 1 over 3. So as you see that if the size of the nucleus grows, then the number of charged particle inside the nucleus increases. So the size increases and the 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 size increases and the nucleus becomes uh, heavy, and then it automatically starts radiating, and the radiation to gain stability, it start radiation nuclear, and it start radiating the nuclear. So this is one of the reason here that the nucleus start radiating, right, in order to gain stability. And this is just done by losing a stored energy in the form of, that is in the form of gamma rays, or by decreasing its size, that is by emitting alpha or beta particle, right? So this is one of the reason here. So the concept of the binding energy comes from here. Now why? Because they look, now since as we have bound them together, as they are being held by strong nuclear force, then work must be done, right? That the to separate them. So as now you have seen that proton and neutron, proton and neutron are bound. They are bound strongly by nuclear force, strongly by nuclear force. So to separate them, so to separate them, so to separate them, work must be done. Work must be, work must be, work must be, to separate them, work must be done. This refers, this refers to the binding energy, to the binding, to the binding energy. This refers to what? This refers to the binding energy. And this binding energy, mathematically, the binding energy, which is the amount of energy required to smash the nucleus, sorry, or to break the nucleus, this binding energy can be calculated by mass defect, as I did it in the previous class, by mass defect n to c square. And that is, there is another term which we call the binding energy per nucleon, that when you separate one nucleon, the amount of energy required. So that is also extremely important, the binding energy per nucleon. So that is R, sometime we call this the packing fraction, the packing fraction. This actually describes or measures, describes or measure the stability, the stability of the stability of the nucleus. Greater this binding energy, greater will be the stability of the. So greater packing fraction means more energy, right? This increases, that is, I will explain this to you from the graph of the binding energy also, and you will see it now. This as I told, that it is the measure of the stability, that is binding energy per nucleon, right? Yeah, greater binding energy per nucleon increases the stability, the stability of the nucleus. It increases the stability of the nucleus. Now, there is there are two important points, and I'm going to explain this to you, that binding energy per nucleon increases when fission occurs, when fission occurs, when fission process occurs. Why? Because, for example, if you have uranium 23592, right? And when this fission means when it splits into two parts, then this has energy equal to what? Its binding energy per nucleon equals roughly 7.5 MeV per nucleon. It is per nucleon. Now after fission, this comes out to be 8.8 MeV per nucleon. Therefore, during fission, energy is released. This is what for the fragment products, right? So that is the binding energy per nucleon. Similarly, in the case of the fusion, this also increases. Now let us see, look at the graph first here. Now you see that this is the binding energy curve. This is, as you see here, look, this is the less tightly bound nuclei, as you see. And here you see the nuclear binding energy. This is for the uranium. This is what the fission. right? That binding energy released when there is the fission process, when a fission process occurs. And here the binding energy is released when there fusion occurs, when two lighter nuclei combines to form a heavy nuclei, or when it breaks, right? So this is here, you just see, look at this region. Now this is the binding energy per nucleon. Now if you just look to the graph here, then definitely at this peak point, the binding energy per nucleon is the highest. And this is what? This is iron. And if you see that it is just between, look, it is just, if you just look, see, this is 50, and see here round about, that might be, if I guess, 60. So you see that between A between 50 and 60, right? This is A. So A between 50 and 60, the binding energy is the highest, and it decreases both on the left and then both on the left and right. So the binding energy shows greater stability. So it means that it is very difficult to smash the iron nucleus. So iron is the most stable. Why? Because it needs a lot of energy to break the nuclei, because this energy is very high here, as you see. Now look, if you see in this graph here, what you see, look, for this reason, iron, as I told, the iron group or isotopes are the most tightly bound. Why? Because the binding energy per nucleon is what? Very high. So greater work must be done to separate the particle. Greater work must be done. But here on the other side, you just see anything on the right side of the iron can be created in a fission nuclear process, which involve heavy atoms splitting into lighter element. This occur in nuclear reactor or in a nuclear bomb. In both fusion and fission reaction, tremendous amount of energy are generated, right? This is on the right. What you see on the left, anything on the left side of the iron can be created in a fusion nuclear process, which involves atom compressing together under extreme pressure and temperature to form a heavy element. This is what it goes in the core of the star. So you have seen that during the making, this is what? This is the making. Here it is what? Making of the nuclei. Here it is what? Breaking. So both in the making and in the breaking, energy is released. Now the question is what? Why? Because when nucleons are combined to form a nucleus, work must be done, right? Work must be what? Work must be done. So that work is stored in them in the form of energy, right? Because energy is neither created nor destroyed, and during this process some of the mass is destroyed. Okay, so now when you combine the nuclei, this thing happens. So when you destroy the nucleus, when you split the nucleus, then what will happen? That is, again, work must be done, energy must be supplied, right? And the energy which they just got in the making will now be released, right? Because, and it will be because some of the mass will be destroyed, and it will be in the form of what? It will be in the form of energy. Here, as I told, that look, for the helium nuclei, what is the mass defect of the helium nuclei? The mass defect of the helium nuclei is this one. So what is the binding energy? The binding energy of the nuclei, as I told, delta mc square, right? So what is the mass? The mass is 0.02943 atomic mass unit. So in order to convert this into energy, so what you will do, you will simply write this mass in the atomic mass units only, and you will multiply by 931 MeV. Why? Because one atomic mass unit is equal to 931 MeV. As I told that when you convert one atomic mass unit into energy, its equivalent is 931 MeV. So when you multiply 0.029434 into 931 MeV, then I think it will be in the range of 28 MeV, I think so. Let me check. let me use my calculator. For example, point, it is 0.02943 into 931. So yes, it is. Here it is 27 and I told 28 MeV. So that will be around 28 MeV of energy. Right. So this is what the binding energy of the helium nucleus. So if you want to break the helium nuclei, at least this much energy will be supplied to it. So this is our today lecture, and that is all about the it is all about the binding energy, right? So the in summarized form, binding energy is in fact the amount of energy required to make or break the nucleus. So thank you very much. So inshallah, see you in the next lecture. This is enough for today.